Ah,
Hello, Denis. Sorry for the joke.
I can.
So it's a pleasure to welcome you at this seminary. I hope we have other occasions to discuss. But so for those who don't know Denis, he is very involved into statistical tests, and so it will be certainly very interested and somehow related to our project. Okay, so thank you, Denis, for learning us, for teaching us.
Thank you, Paul, for your invitation. So this is the title is very short, but the title means that we want to test equality of copulas, and actually of more than two copulas. So this is a joint work with Yves Ngounou. He is a PhD student at Marseille. USM, it's Institute of Mathematics of Marseille. And I also work at ISFA, at the lab SAF. So this talk is on copulas and on the construction of a test to compare simultaneously various copulas. The outline is the following. I will start with just an introduction on copulas and for notation also. I will try to make a link between copulas and ecology. Then I will present a very important tool that is copular coefficients that we will use to construct a test to compare these coefficients and then to compare copulas. And we will start with the two sample case, and then we will generalize this case to the case sample with k greater than 2. And I will try to show you an illustration and maybe some extension. Okay, so this is so why copulas. So I start with notation and maybe a few definitions, but not very rigorous definitions, because I think that you know what is copular. What we can see, if you have a vector of dimension p, say x, and if I denote fx, the joint PDF of x, and f1, the margin associated to x1, and fp, the margin associated to the p's element, then you assume that this random vector variable is continuous. You can construct, you can write your joint probability distribution function as a function of the margins of PDF. And this function C is a copular associated to X or to Fdx. So copulars are very important because they can describe the dependence between all these components of X. And what is interesting, you can make the following transformation. So if you write U, the transformation f of x, so this is the margin, so U j is fj of xj. This is obviously a uniform random variable, and you keep the same structure of dependence after this transformation, and you have again the joint PDF of the vector U, which is related to all margins, because this is uniform, that this margin is just identity. And so you keep the same copula, you keep the same structure of dependence of your vector. And we will use this property to construct the test to compare copulas later. Okay, so this is for notation. So U will be this transformation. So the vector U is a vector with uniform variable, but with the same dependence of the initial random vector X. if you use the derivative of this equality, you obtain what we call the density copular. And of course, if you use the derivative of the PDF, you obtain the joint density of U. So you have also this equality. So this equality is for the PDF and the copula, and this equality is for the density function and the density copula. Okay, so this is for notation. Now, what is interesting, why copula can be used in ecology. So I am not a specialist in ecology, but I've tried to find a few examples. So I give you here an idea of examples. This is some works that I found when I was looking for copulas in ecology, and you can see that I didn't find a lot of works first, and also these works are quite recent. So this, the last one is a review about why copula are necessary in ecology. I just here write the sentence that I found in the review. So these authors think that copulas are very important for ecologists, for analysis in ecology. Why? So I'm trying after to show you a few examples. Why? It's because there is no only correlation between processes in ecology. There is more than correlation. What is important also is the dependence between environment, between species or plants or vegetations. And I will try to show you why it is important to go up to the correlation. So first, there is the Liebig's law. So this idea is that in the Liebig's law, when you have, I give you here an example. If you have, for instance, a plant and you want to see the growth of the plant, maybe this plant depends of many factors, as the sun, the water, but there is one factor usually, but is more important because this factor is rare, and if you have absence of this factor, then the plant can't grow. So the idea is the Liebig's law is sometimes you have many factors, but just a few factors are important at the beginning of the growth. So I give you, to understand, I give you this graph. So you can see here that this is the nitrogen in the soil. And what you can see is here is the growth of the plant. So you can see that if you have not enough nitrogen, then the growth is impossible. Okay, so the plant needs a minimum level of nitrogen in the soil. And after, so there is a kind of correlation here, a strong correlation. And after a certain level, then you have enough nitrogen, and now the growth can be adapted to other factors. But so this is the idea of the Liebig's law. There is a factor very rare and very important, but at the beginning change the relation with other factors. So you can think that in the left side of the distribution of the growth, there is a strong dependence with this factor, okay. But after in the right tail, there is another dependence. We can think also at the Moran effect in ecology. The Moran effect, the idea is sometimes it's called spatial synchronicity or synchrony. It means that the example is if you have two spaces in two environments, usually you think the Moran effect says that the dependence between the two spaces or the two planes, this dependence is the same that the dependence between their environments. So if you know the dependence between two environments, then you can find you can find the dependence between the two species of the tokens. Okay, that's a kind of spatial effect also. One more example in ecology is the following. So here, this is an interesting example, because maybe there is one question, no? In the conversation.
I just wanted to mention that last week there was a talk by Yuri Lember, who was dedicated to these Moran models. So that's just to say that we are speaking the same.
Okay.
Thank you.
Maybe you know more thing about Moran effect than me.
Professor Lambert and also Thierry Villiers, who couldn't attend, know a lot of it. Yes.
Okay, so one other example is this example that characterize epidemics. For instance, when you have different pest species, and if they are very strongly related in the right tail of their distribution, then when you have a lot of species, you have also a lot of another microbe or species, then it can produce an epidemic, of course. So this is important to understand what is the dependence on the right tail of the distributions. And you see that if you have a strong also dependence in the left tail of the distribution, then it happens nothing, because if you have not the presence of the pest species, then you have no epidemic. So sometimes it's more interesting to know what is the effect on the left tail than on the right tail or conversely. Just to finish about ecology, there is a very classical law that is natural law, that is a law of competitor and dominant species. So if you have two species, and usually one is stronger than the other one, and you have such a relation. So this is this graph. So you can understand here that the species 1 are stronger and then dominant with respect to species 2, because you can see that if you have more species 1, then you have less species 2. Is true? Or yes, exactly. And then this is a classical law in ecology, and this is interesting to see what happens at the right tail of the distribution of the species 1. So this is a quite natural law, but actually this is not always true, and there is a very famous paradox called the phytoplankton paradox. So phytoplankton, these are microorganisms in the water. This is a very important subject because phytoplankton can produce 80% of the oxygen on the planet. So this is very important. It has a very important role in the regulation of oxygen, of environment and ecology. Here are different forms of phytoplankton. You have a lot of different species. And you can see that their forms are really different. And one interesting question is, okay, sure, they have known that the abundance of phytoplankton are not necessarily the same, but maybe phytoplankton, abundance of phytoplankton, can be related in the same manner with the environment. So at Marseille, there is a Mediterranean Institute of Oceanography, and they work on phytoplankton. They have what we call flowcytometry. This is captured in the sea or with a boat, and they can have many data about phytoplankton. giving the abundance of phytoplankton, and also they know the salinity, the temperatures, many things of many other variables. And there is a project, it will start in 2 years, to add to such data satellite data. This is called SWOT, or surface water ocean topography. And so you can understand that there is a very important study, but we record a lot of data. And also the idea is to understand the relations, the dependence between phytoplankton, the evolution of phytoplankton, and environmental or climatic data. And the paradox of the phytoplankton, excuse me, I forgot, it's that this is surprisingly, phytoplankton, when you have different species, these species can grow together. There is no dominance of one species with respect to another one. This is the converse of the classical law of dominance or of competitor in ecology. So this is not so easy to understand phytoplankton, and you have many studies to understand relation and dependence with other variables. So now, when you have understand that the problem is to you have more data, you have also more dimension. And one problem is to understand the relation, the dependence with such data with other data. So you can think about analysis simultaneously such data. Okay, these data can come from different captors. Also, there are different scales, different shapes. So the problem can be not to compare their distribution, but to understand the dependence. Okay, so to understand their comportment with respect to other variables, and this idea is translated in terms of copulae. Okay, so this is the main purpose of this talk, is to compare the dependence of different forms or different species or different varieties in different populations. Okay, so this is exactly what I want to do here. That is to construct a test of comparison for different dependence, for different populations, for different populations. Okay, so I start with the first very short review, just to say that in the one sample case, when you have just one population and you want to construct a goodness of fit test for copula, there are many papers about this problem, and I just give you a reference because this is the last one that I found. This is a reference in Bernoulli, where you can find other references. Okay, in the two sample case, actually there is just one work, I think, to my knowledge. There is one work from Rémillard and Scaillier, and this work can be done for paired populations. So, and this work proposes the test to compare two copulas. Okay, there is a package, so this work is very used. And when you want to compare two copulas, you usually use the Rémillard and Scaillier test. So in this talk, we want to propose another construction to compare copulas, and I thought we would like to extend the two sample case to the K sample case. Okay, so now I introduce notation to understand the construction of the test. So we assume that we have K populations, and for each population, we have an IID sample. These populations can be paired, okay, it can be dependent. So it could be the same population, but at different times that you observe. And then we denote by C1, C2, Ck, the copulas associated to the 1 to K population. And our problem is to test the equality, the simultaneously equality of all copulas, okay, against various difference in these copulas. Okay, so remember that at the beginning of the talk, I changed my random variable x, putting f of x, and then obtaining a uniform distribution u. And remember that u is uniform, so we can use an expansion in an orthogonal basis of Legendre polynomials. So this is what I'm writing here, where these coefficients rho are just the expectation between LG1, this is G1's degrees Legendre polynomial, J2, JD is JD's degrees Legendre polynomial. So you can see that these rho coefficients actually they characterize the density because this is an orthogonal basis. And more, you can see that this is actually correlations, but correlations with higher moments, higher order. So if you have just two, first two polynomials for just two random variables, it will be just two correlation. If you add another polynomial, you have kind of correlation with order 3 and so on. And what is interesting, if you remember, the density, the joint density of U, this is exactly the copula density. That's the first, the second slide that I show you. So this joint density is the copula density. Then I can rewrite this equality in form of density copula, and then the density copula of my vector x can be written as follows with such expansion, and then you can come back to the original copula, and then the copula finally can be written as with this form. And so what you can see that here you have the case where the copula coincides with the independence case. Okay, so this is a product of the PDF if you have independence. It means that all coefficients in that case are 0, but of course, because they are just correlations between all order of your vector. And this quantity I of j are very easy to compute because this is just the integrals of the Legendre polynomials. Okay, so now what we have seen with such equalities, it is clear that the second row characterize the copula, and we call it copula coefficients. So the comparison of copulas finally is equivalent to the comparison of such coefficients. So that's the idea. We change the null hypothesis, and then we change copulas by their coefficients. So now the null hypothesis is just the equality of all coefficients. So of course, this is not a finite hypothesis because this equality must be satisfied for all j, for all integer j, j1 up to j. P is the dimension of the vector. Okay, so this is the problem. So we want now to test the equality. So of course, this is difficult to compare an infinity of coefficients, but we will compare a finite number of coefficients. But this number can tend to infinity with the sample size. Okay, so when n sample size tends to infinity, we will consider an infinity of coefficients. That's the first idea. The second idea is that okay, but can we compare simultaneously all these coefficients? Actually, no. We just start with 2 by 2 coefficients, and we will have that rule to select automatically the best coefficient. Okay, so that's the basic idea. Now, first, how to estimate these coefficients? That's very easy because these coefficients, remember, excuse me, just up. This is here. Okay, so these coefficients are just expectation. Okay, expectation. Okay, but so you are transformation by the PDF. So we don't know the PDF. So we have 2 empirical transformation to do. This is expectation, so empirical moments, say, and the moments of PDF. So we change PDF by empirical PDF. So here are notations. we consider k random vectors from k populations denoted by x1, this is the first vector, xk, this is the last vector, okay? F1 is for population 1, this is PDF. Fk is for population k, okay? And C1 is popular for population 1, Ck is popular for population k. And now we observe for each population, we have a 9ID sample of size N1 for the first population, up to Nk for the case population. We have classical conditions on the sample size. Anyway, I will just to simplify. I will show you the case where all populations are dependent, are paired. So I assume that N1 is equal to N2 is equal to Nk. That's what I said. It could be the case if you observe the population during different times. So you have time 1, time 2, time k, and this is the same population, then the same size. Okay, so when this index k, this is for the case population, and we want to transform again this observation by the PDF. Of course, we don't know the PDF, so we have to estimate the PDF. We use the empirical probability distribution function here, okay? So u at u, this is just the empirical PDF applied to x, okay? And then we can estimate very easily the copular coefficients, just taking the empirical moments of this random variables, where f is replaced by f at f. Okay, so now we can estimate these copular coefficients. We want to compare such coefficients. So the idea is to use difference 2 by 2, okay? So for the L population versus the M's population, I want to compute the difference between all coefficients of the L's population against the M's population. So under the null, these coefficients must be equal, so this difference should be close to 0, and under alternatives, this difference can explain. Okay. Now just the problem now is okay. Now the problem is we want to compare these coefficients for all j. For all j are integers in n p, so are vectors of dimension p of integers. So we have to order these coefficients to start by the first one, we compare the first one, okay. We continue, we compare the second one, we continue the third one, but since we have a vector, we just introduce a kind of lexicographical order, but it's very natural. So maybe I can just show you the next slide to be more clear. Just this. Here, G, this is a total order. This is a number of, if J is the degree of the legend, of the product of legend polynomials, you have a total order. This is the product of the first one plus the product of the second one. So this is a total order of polynomials. And the idea is to select, to have an order to select the group coefficients. So the order is the following one. We exclude the case where all polynomials are 0 except 1, because in that case, it gives 0. So this is an obvious case, not important to compare. So we just put this order. So when you have, for instance, a total order equal to D, the first, when you have a vector of dimension P, then the first total order equal to D, the first is the vector D minus 1, 1, okay? The second is D minus 1, 0, 1. The third is D minus 1, 0, 0, 1, and so on. And the last one is 0, 0, 0, 1, D minus 1. So this is a very natural order. And now we can can compare in this order the coefficients. Here I just give an example. If you have just to divariate the variant vector, okay, if p is equal to 2, then if p is equal to 2, total order for 2 dimensions, it's just 1, 1. Okay, polynomials of total order 2 in x, y is just x squared or y squared or x times y. But we have excluded the case 2 x squared or y squared. But there is only 1, 1. This is the same thing example here for if d is equal to 3, then if the total order is 3, then you can have 2, 1, 1, 2, because 0, 3 or 3, 0 are excluded. Okay, so this is okay. This is just notation, and you have to organize the test. But this is very easy to understand. Then finally, now that we have an order on the polynomials, I would like also on copular coefficients, because copular coefficients are directly related to these polynomials. Now that I can order the copular coefficients, I start with the 2 samples to construct a test of comparison of 2 copulars. So I just want here to compare the first copular to the second one population against one other population. Okay, so I just assume that n1 is equal to n2 equal to n, so the population can be paired here. And the first statistic that I propose is just the difference of copular coefficients, the first one, okay, and then I had the second one, and then I had, and you can see that all of these statistics are embedded, okay? You can see that each time I had a new copular coefficients. In which order? The order that I showed just before. So just to understand, the idea is to compute all difference of copular coefficients in the order that I proposed just before. Okay. And just to simplify, we write V1, the first difference of coefficients, V2, the first plus the second one. It's important to see that each time you have plus, if k increases, then this sum increases, and then you can see that you add each time the difference. This is not just one difference or 1 over. This is 1 plus the second one plus. Okay. So now, how to choose k, which is a good statistic to compare my copulars. And so we want to propose an automatic procedure. What is clear is that V is an increasing sequence of statistics, because each time I had a positive value, n times the square of this difference. So this is an increasing sequence, and to choose the good statistic, the idea is to use penalization, like a Schwartz penalization. So the idea is to choose the biggest statistic, but up to a penalization, okay? Because always the statistics increase, so you have to consider that here you have k different copular coefficients, so you have k square of difference. Then we use this penalization, k times log n. Log n is not necessary. Actually, you must have something that is a potato of n power epsilon. But log n, it works. Okay. What is important also is that you have here the n, that is the number of statistics that we can go. So we can go up to infinity when n tends to infinity, okay? And our statistic is a data-driven statistic, because now this can choose automatically the bigger statistic, so Argmax, when you have took into account your penalization. This rate Dn must satisfy such assumption that I call A, but this is our decision, so I choose Dn. Okay, this is my construction of the test, but the construction must satisfy such rate. Okay, and we have the following result. So this is interesting because when n tends to infinity, the selection, if you are under the null, it means that all coefficients are the same. So all difference are close to 0, okay? And there is a convergence of this. There is a kind of central limit theorem. And then when you consider n times the square, you have a convergence in probability. And then this, when you had another difference, you had finally something that is convergent. So it will not be greater than the penalty. That is the idea. So since you are under the null, all copula coefficients are the same. The difference are quite noisy, and then you select only the first statistic. Okay, just so Dn tends to 1, and then the asymptotic distribution under the null of our test statistic is just V1, the first one, that is T to 1. We are comparing the population 1 against population 2. That is n times the difference of the first coefficient copula. And the first coefficient copula, if you remember, I showed you in the little example, but just 1, 1. So this is just the expectation of L1 times L1 U1 times L1 U2, but actually just a correlation between U1 and U2. Okay, so now we have this result. So we have just to compute the distribution, asymptotic distribution of V1. And this is done here. So you can see that V1 is this is the root of n times Rj square. So we have just, I just delete the square, and this under the null converge to a normal distribution with variance here, but variance, okay, this is just to show you that we know what is the variance, okay, this is not, we have no time to see the variance now. And what is interesting is that we know how to estimate this variance. We have a convergent estimator of this variance, okay, that we call at sigma square, okay. So this is, again, not very important here to see that, okay. Just we know how to estimate this variance. And then finally, we know that Dn will choose the first statistic. We know that this third statistic is asymptotically normally distributed. We know the variance. We can estimate this variance because we have a convergent estimator. Then finally, we obtain this statistic. This is our test statistic for the two samples, again, two samples. And we know that this statistic under the null converges to a chi-square distribution. So this is the first step. We have finished with the two sample result. And now we want to extend this two sample case to the k sample case, the k greater than 2. Okay, so what we do, that's quite the same idea, but now it's more easy actually because we have a finite number of populations. We have k populations. Okay, so I want to compare now first population against second population. Then first population, again, third population. But in such way that I again use an order, and I will use a second penalization to select automatically the good, the best difference between my two populations. So the idea is to, I fix n1 is equal to n2 equal to nk for simplification of notation. So these populations can be dependent. And here, this is this slide is just to say the following, that is more clear, I think. How we proceed now? We want to construct, again, a series of statistics that will be embedded. And the first one will be population 1 against population 2. This is like the first element of the triangular matrix here. Then if I read so from left to right and from up to down, the first one is population 1 against population 2. The second one is population 1 against population 2. The third one is 1 against 4 and so on. And the case 1 is 1 against k. No, the k minus 1 is 1 against k. Then the k1 is 2 against 3 and so on. So this is 1, 2, 2, okay? So this is natural order. And when I have seen this order, I understand this order, okay, I can now construct my sequence of statistics. They are all embedded again. So V1 is a previous statistic to compare one population against population 2. Okay, this is just what we have done before for two sample cases. Now V2, this is this first statistic plus 1 against 3. And the order is the same but in the triangular matrix. Okay, so V3 is V12 plus V13 plus V14 and so on. And the last one, this is a finite number here. We have no infinite population, number of population, but it could be the case. I will come back later. Now we have to decide which statistics can express which hypothesis, H0 or H1. So the choice now is again a choice with penalty. So the idea now is to choose the statistic, okay, V1, V2, which maximize such criteria, okay. So we want the greater statistic to understand that there is the greater difference, but we know that all statistics are increasing because they are embedded. So we add penalization. So VK contains K sub-statistics. So we use this penalization, K times log n. Again, log n will be discussed. It works with log n. And finally, we obtain a similar result that previously, but now for the K sample. This rule of selection under the null will tend to 1. So finally, in the K sample case, okay, in the K sample case, if all populations have the same populace, then the statistics will tend to the first one. Okay, it means that doesn't mind what are the difference. Okay, anyway, all difference are kind of noise, or anyway it tends to 0. Okay, so faster than log n, and then you decide to just keep the first one. So it's perfect because we know the distribution of V1. Okay, so now we have just S1, and so we understand that our statistics is the same as the previous one, the first one. Okay, the criteria is not the same here because Sn now depends on the number of components of population, sorry, and the number of components of polynomials that can tend to infinity. And we have our final statistics that has a chi-square distribution under the. So just to say a few words, I don't know what time. Okay, I have 5-10 minutes again. Maybe. So a few words about.
Time you want, I'm sorry.
Sorry.
Just take the time you want. Okay,
so 1 hour again. Thank you. No, 5 minutes, it's okay. No, 10 minutes maybe. So just to say that alternative, the test is convergent again alternative. If you have one copula that is different, if it is the case population in the order of population, remember the of the triangular matrix. If this is the order, if for this order there is a difference of two populations, then your automatic selection will select this order. So you know that it is here that there is inference. And the statistic will tend to infinity. So the test is convergent against all such alternatives. Okay, so to just a sketch of the proof, the idea that was, okay, under the null to prove that Dn tends to 1, so that this probability tends to 0. So we have a first inequality, and now the idea is to prove that this is slower than log n, okay? And then we decompose such difference of copula coefficients into different copula coefficients. Under the null, you have a good property, and the problem that was, you know that you don't know the PDF, so you use the empirical distribution function. So you can decompose the empirical distribution functions against the true distribution functions, okay? And when you do that, after you can use the properties of Legendre polynomials and the classical Green-Cook and Feli theorem to obtain the result for the convergence of the n to 1. The asymptotic normality was more difficult, and finally we found a result of Bejong-Kuhl in an old result, and we adapt this result to get the normality of the asymptotic normality of the statistics. Okay, and just generalization of the K sample was very easy because we have finite number of samples, so it was easy. But we could extend this result very. I think that it's easy to extend this result to the case where the number of population tends also to infinity with the sample size. It would be possible. And also, another remark is that we could also consider contiguous alternatives and not just roof alternative, which say that C1 is different from C2. Okay. Now, just to illustrate this approach, this is a very, very cool example, but you know the IRIS data. But this is new because nobody, I think, tried to compare the populace associated to IRIS data because this test is new. Look, I hope that nobody have done this. So you have, you know, this is the length of sepal, of petals. You have also the width of sepal and petal for 3 populations, population setosa, versicolor, and virginica. So you have 3 populations and a vector of dimension 4. And you want to know if, for instance, you can be interested in the dependence, not the distribution, of course, but the dependence between this vector for the 3 populations. Of course, the distributions are not the same. Here is the distribution of the vector of the setosa, donc petal, sepal length, sepal width, petal length, petal width. This is the distribution for this versicolor, so it's clear that this is not the same on the box plot, but it is clear that this is not the same distribution. Okay, you have not the same joint PDF for sepolar, versicolor, or virginica. Okay, but maybe you could have the same dependence between petal and sepal. Okay. Actually, no. We use our test procedure, and we obtain a p-value very close to 0. Okay, so this is clearly not the same populace. Okay. Well, now the statistic value is very large, 10 or 12. Now, just a remark, we can do like in an ANOVA test, we can do now a 2x2 test. See if when you have rejected the equality, maybe you can compare 2x2. Okay, that's what we have done, but there is again p-value very close to 0. So we are sure that there is no same dependence between these populations. Okay, so that was just to give you an illustration. Okay, we can also compare the number of polynomials that have been selected, the value of the statistic. Okay, just to finish, one idea of clustering, very quick. So yeah, this case simple procedure can be used, and we have, this is a work in progress. So what is the idea? Okay, you have K population. Imagine that you have K population of phytoplankton. and with vector with different environmental variables, and you want to know if the dependence is the same. Okay, you just choose the two populations that are closest. So the closest population, say A and B. Closest in which terms? In terms of the statistic for the two samples. So you compute all two sample statistics and you choose the closest, okay? The smallest. Okay, you compare these two. If you accept, you have the first group and you continue. You now select the third population, the population with the smallest statistic with respect to A or B. Okay. So you have to be the one element closest to one element of the set. And then you test the ability and you continue. If you accept, your group is growing. And if you reject, then you have finished your first group and you continue with this other population. So this is a data-driven automatic clustering. You just have to decide which is the level of the test. Okay, so to finish conclusion, so we have done many simulations. This is not completely finished, so, but that was boring, so I didn't show you the simulation. But in the two sample case, we get as good or maybe better results than for the for the classical two sample case that exist from linear escalier. And for the case sample case, anyway, we have no competitors. We don't know. But it seems to work very well. The package is in progress. Actually, we have in the package estimation of the copular coefficients, and also it gives an estimation of the copular, and we are working on the construction of the test. To finish, just to say that copular coefficients are very close to Kendall, Stowe, and Spearman-Grove. So you can. This is maybe a way to construct test and estimation of such coefficients. And finally, also these copular coefficients are very easy to adapt to construct the test of independence, and we are working on this project actually. And thank you very much. I hope that was not too long, but it's okay. It's okay. Thank you very much.
Okay, thank you. Thank you. Are there questions or comments?
Yes, so you presented the legend expansion. Now, I worked on a different characterization for copulas. I wonder if you're familiar with that, because that might also be a source of some tests. It's on a paper with Rustam Ibragimov. I posted it in the yeah.
Okay.
I'm sorry, you didn't post it to everyone, but just to me.
No.
Oh, okay. Well,
okay, I can send it to everyone.
Yeah, okay, I'm looking for the discussion, but okay. Alors, so maybe the originality of this Legendre expansion is that we use it for the density copula, not for the copula. And what is interesting, if you use it for the density copula, and after you come back to the copula, you have a nice expression. If you try to use this expansion directly to the copula, so it's easy because copula is, you're sure that it's bounded, the PDF is bounded, so you have an expansion, but the coefficient of this expansion are not very easy to use. You see what I mean? The idea was to use such expansion for the density copula, not directly for the copula. Because if you try directly for the copula, you have not a nice expression of this coefficient. So you can use Legendre polynomials or every expansion for the copula, but I'm not sure that you could play with such coefficients so easily.
Yes. Well,
because I have seen.
I think that, I mean, I don't think, I just posted it for you, you know, in case you were not aware of it. I don't think, okay. I think that your work is unique and very interesting. And I'm not sure that, you know, this characterization that I posted will be of any.
I will look. I see the paper now. Okay, I will have a look to this paper. Yes. Okay.
Well, I thought, you know, since we're trying to get interactions, this is one try for an interaction. I found your talk fascinating and very illuminating. I'm very glad to see that people are in ecology are looking into it. So I'm looking forward to working on that. So thank you very much. Very interesting talk.
Okay,
So,
thank you.
so
I have a question.
please.
So thanks for the talk. Denys. Yeah, I was wondering something about some modification, because many times I suppose that if you test equality between many population, you will reject the test. But maybe there is something which is more flexible, in the sense that you can test the adequacy to, for instance, a parametric family. To test, for instance, if you take several ecological systems and you have, for instance, the same kind of family, such as the Gaussian family. So I suppose that if you modify your test with respect to this, it should be possible to compute the raw coefficient in terms of the final parameter, something like this.
Yes, yes, you're right, because you were, yeah, okay, I see. Because you will have, maybe if you have a Gaussian, you can use, for instance, another basis, and you can have expansion, you will have expectation of, for instance, Hermite polynomials of U and something like that. Yes, you're right. Okay, yes, you're right. But I'm. This is more for the one sample case in the parametric case. You mean that if you have a k sample case in parametric case, maybe it is equivalent to compare just coefficients, no?
Yeah.
If you show that you have the same family.
What should be expected is that you have exactly the same shape, but different correlation metrics, for instance.
Okay. Yeah.
But I don't know. Maybe you can use all the data instead of making the test one by one, because yeah, you can test if it is Gaussian, and then another one if it is Gaussian. But I don't know.
Okay. Yeah. But there exist many tests for the one sample in a non-parametric case for the one sample to say yes, this is popular in this family. There exists a lot of works.
So yes, okay. So thank you very much. I think that's a very nice talk, and there are many things to do with your ideas. That's always that's again an idea that we used together in several papers, but
Okay, yes.
it's very productive. And may I ask just about the fact that you are working with independent samples, and is there a chance to extend the central limit theorem for the dependent cases? Or I don't know this paper basis of 64. I don't know at all.
First, we have independent samples for one population, but populations can be paired. Okay, but you're right. If we have dependence in intradependence in the population, I don't know because this is vector, so I don't know. It could be interesting. I don't know. Okay, it could be interesting.
I don't know if there are other comments.
Yes, in the paper I sent, there's a section on doing conversions for dependent sequences by using a type of Pearson correlation coefficient.
Okay.
So it's towards the end of the paper. So that's I cannot. It's at the very end of the paper. So it's basically using. Yeah, let's continue. If you have time, keep on going, please. More. It's a very long paper. I'm sorry.
Oh, I see. Okay. Maybe tonight.
Okay, so we are almost okay. Let's stop a little bit before. Okay, you see here. There's theorem 7.2. So you have Pearson, an extension of Pearson correlation coefficient, and
okay, I see. Yeah. Okay.
then you have conversions in distribution. So if you calculate the Pearson correlation coefficient and those go to zero, then if you know that the case of independence holds, then the case of your dependent holds. So that's what it is. So anyways, that's one way of approaching that problem. But you know, it's
Okay.
I don't know if this answers Paul's question, but I just wanted to point out there's something easy
Okay.
to understand. Yeah,
okay.
there's something easy to understand, an inequality. Can you move it forward, Paul, a little bit?
Where?
Forward a little bit. A little bit. Okay, right here, right here. One more. I'm sorry, I'm taking your time. Okay, here. You see, here is a very interesting, I think, inequality that is not known. But you suppose you have any vector of variables, dependent variables,
Yeah.
and you want to estimate the probability of any function of that vector bigger than x. Then that's bounded by the probability of the same function of independent variables with the same marginals plus the Pearson correlation coefficient times the probability of the square root. So if you know what the tail probability of your independent variables is, you can get a sense as to what the tail probability of your dependent variables is. Anyways,
Okay.
No, it will be very nice to go ahead in this direction. I think maybe I just
I will have a look to this paper.
I don't know because maybe I stop recording now, but it doesn't mean that